All right, so don't know exactly how this is going to pace out, but do as much as we can here. All right, let's talk about theory of relativity. Now we're going to start with just plain Newtonian relativity. When people say theory of relativity, they're really talking about like Einstein physics, but we're going to start way back before that, with just plain Newtonian relativity, nothing crazy. Okay? So I got a guy in a lake versus a guy in a river that has a current going 2 meters per second downstream, like that. Okay. Let's say these two start out in the lake together and they race back and forth. So they're going from the start finish line to this tree at the end of the lake and then back, and they keep tying because they're like equally fast paddlers. Okay. But if you put this guy in the current, now who's going to win? Now I know the answer is obviously up here, but you do distance equals speed times time. Rearrange that solve for time because they're going the same distance, but maybe different relative speeds. Okay. So isn't it true the guy's paddling speed, which might be 10 meters per second, plus the current would give 12 meters per second relative to this tree? Right? And he's coming back to be 10 minus 2. That's where I'm getting the 8. Right? Now, these are relative. So this guy paddling relative to the water is always 10 meters per second because they're paddling the same. Right? But then the current relative to the land, therefore, what's the boat relative to the land or relative to the street? And that's where the 12 and the 8 come from. Okay? Now, you can show it doesn't actually matter what the speed of the current is. The guy in the lake will always win that race. Right? Now, I just threw in some numbers just to give you guys a numerical example. Okay? But 25 seconds is longer than 24 seconds. So the guy in the lake wins the race. You guys see that? Okay? Right? Now, hold on to that idea. Right? When you have something moving relative to something, because that's going to be important well, later. Okay? Okay, here's another version, really similar idea. Is let's say you got a moving truck. Let's say the truck's going 10 meters per second to the right. Okay? And you could throw a baseball at 40 meters per second. So you can see the velocity of the ball relative to the truck is, well, maybe I should say speed. Right? But either way, it's going to be 40 meters per second. This guy can throw at 40 meters per second. Okay. Now, if you had a radar gun on board the truck, even if the truck's in motion, you point it at the baseball, it doesn't matter which direction you throw the baseball, it's always going to read 40 meters per second. Okay? But if you're this guy in the blue hat on the ground, that's not going to be the case. So this guy's catching the ball. Well, if the truck's moving forward, don't you have to say 40 plus 10 would be 50? Or in this case, 40 minus 10 would be 30? Right? So nothing crazy, nothing crazy. Right? You guys could do that anyway. Right? But hold on to the idea. Right? Now, let's talk about light. And what is the speed of light and how long have people known this for? So there's a fun history of this. You can go back to, there was a Danish physicist named Old Romer back in, I think, 1600s. He was looking at, I think it was Io orbiting Jupiter, right? And realized that as Earth was heading towards it, it looked like it sped up a little bit, and Earth was headed away. It looked like it slowed down a little bit. He was able to apply essentially like a Doppler effect to that situation and get kind of a ballpark idea of the speed of light, but it wasn't super accurate. But the first time that we accurately knew the speed of light was actually before the Civil War. This 1849, a guy named Armand Fizeau was over in Paris. And he realized he could set this experiment with this cogwheel. He could get the cogwheel spinning. So he's got some light source here, and here's the eyeball to represent like an observer. Okay? And then way off in the distance, several kilometers away, he has a reflector, a mirror. Right? So this D might be like several kilometers. And that light would have to travel to the mirror and back. Now, sometimes some of these light rays, I'm just showing one light ray, right? But bajillion light rays. Some of those light rays hit these teeth and don't even reach the mirror at all. And some go through the gap and then they reflect back. And if it's not spinning, still go through the gap and then you can see the reflection, right? That's all I'm here. But what if you get this wheel spinning so fast that by the time this light ray makes a return trip, where there used to be a gap is now a tooth and vice versa? Well, that means that this observer would not see the reflection at all. So as you spin up this cogwheel, you guys see this omega for angular velocity? So you spin it faster, 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 faster. Okay. And right at a certain angular speed, you can see it will look like a door is closing on that reflection. Okay? And if you match it right there and say how fast is it spinning, there's enough information there where you can calculate the speed of light. And I have a proof over here. So it goes, this is in order. So blah, 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 blah. And here's the answer right here for speed of light. And today we know it's like 2,998. It's like 3 times 10 to the 8 meters per second. Like, how do we know that? Because this right here. So we know. All right, so let's hold on to that. Now we know the speed of light. Right? Okay. So fast forward a few decades, 1887. Now, what's people's thinking at the time around the 1880s? They're saying, well, I know light's a wave, and I know that because you can say like cut a few slits in a card, shine a light through, it creates an interference pattern. Right? What distinguishes a particle from a wave? Well, particles just move like bullets in straight lines, and waves create ripples that can interfere and create interference patterns. Right? So light must be a wave. And oh, well, I know sound waves have to have a medium to travel through. Guys, how are you hearing me right now? Is my voice traveling through the air in this room? Right, and it's really pressure waves, right? It's like longitudinal, right? This whole thing. what if you were in space? Can you hear anything in space? No, because there's no medium to transfer the sound, right? Now, back in the 1880s, people's logical thought was that, well, light must work the same way, right? You know, it must have some kind of medium, right? And they call that medium an ether or a luminiferous ether. And if that was true, then there must be some relative motion between the Earth and that ether. Would make sense, right? Now, if you've never seen that term before in a science book, then that's because this experiment unintentionally disproved that. But I got to build up to that. They think, well, the Earth is spinning, so maybe like during the night or during the day, it would be like the face of the Earth would be traveling opposite directions, wouldn't it? Right? And what about from summer to winter as the Earth revolves around to the opposite side of the sun, right? So if we're all sitting in this ether, then there should be some kind of relative motion between us and the ether, kind of like we're like in a giant swimming pool, right? You should be able to detect that. Right? So what we're going to do is we're going to have some light source here. We'll have this half silvered mirror. When I say half silver, some light can travel through, but some like half of it reflects off. Right, and it'll have a couple mirrors over here that are equidistant. Okay? So I got two light rays. Right, so one passes through, bounces off this mirror, then reflects this way and goes to this observer. Okay? The other reflects off this mirror and then off this mirror and then passes through. Okay? And what they were thinking was, well, the one that goes east-west, that's kind of like if I scroll back a few slides, that's kind of like more analogous to the sky in the river, right? Because if the Earth is spinning towards the east, or traveling faster east than west, right? The light goes east, but then it goes west. That's kind of like the scenario down here. You got sky in the green hat. But the light ray that bounces north and south, that's more analogous to get the guy in the lake because that would be perpendicular to the spinning of the Earth, right? And also the revolution of the Earth around the sun. Also, it's all kind of on the same plane. Right? So they were expecting these light rays to reach this observation point at slightly different times, slightly out of sync. But that's not what they got. They got that they were in sync. So, okay, so now what? Okay, well, let's just try this maybe a few hours later in the day or at night, or how about a different season from summer to fall to winter, right? But it didn't matter what time of the day or what time of the year they tried this out. They always got these light rays were in sync. Right? And that led to the conclusion that there is no luminiferous ether, that light can travel through the vacuum of space. All right, so is that okay? Right, so electromagnetic waves can travel through the vacuum of space. Right? Now hold on to that. All right. Now what? Okay, so we're going to fast forward a bit to around the early 1900s, like leading up to 1905. Einstein's thinking about this, right? And some similar experiments, and he realizes that the way that like this Newtonian model of the universe would actually be not consistent with that experiment, and that this has a really profound outcome. So what he's saying is that so this is like Einstein's thought now is if you go back to that truck, but instead of throwing the ball around, you guys remember the ball, the velocity is added and subtracted like Newtonian style. Okay, okay. Got 40 plus 10 and 40 minus 10. Okay. Suppose you gave each of these guys a cogwheel. You have it doesn't matter how fast the truck's moving. The truck could be moving like the speed here or like half the speed of light. Okay? These guys are always going to get the same speed. Right? To get exactly there's the exact speed of light down to the meter per second. Okay? That's like defined as the speed of light. Okay? Doesn't matter. Now people kind of knew this, but they weren't thinking about the full implications of what that would really mean. And what Einstein realized is if you have two observers that are watching the same light, they're getting the same speed, that because maybe one observer is in motion and the other is not, they would be seeing that light move different distances. So how about this? Let's put a guy on a train. I'm going to maybe change that story to a rocket later, but Einstein liked trains at the time, so got a guy on a train. Okay. Versus a guy out on land. Nothing to do. Okay. So this guy hops in a train, and it's supposed to have a light source on the bottom, his flashlight. I got a mirror on the top. Okay? And we're going to watch a ray of light go straight up and down. Well, it would go straight up and down if you're inside the train. That's all you see it do, right? You watch the individual photons, they go straight up and down, break out your cogwheel, measure the speed of light, get the speed of light. Okay? But this guy with the green hat outside, he's not moving. But he watches the train go by. Doesn't he actually see that same ray light actually travels diagonal path? That'd be true, right? Oh, but again, if this guy also has his cogwheel and they both agree on what the speed of light is, even though they see the light travel different distances. And what Einstein concludes then, and I bet you guys can figure this out too, is if they see the light travel different distances, but they report the same speed, that means that these two characters must be experiencing different what? Huh? Times, different passages of time. Okay? And you can set up this Pythagorean theorem. Guys, does this look like a right triangle right here? Pythagorean theorem. Okay? So you do a squared plus b squared is c squared, which is what I have in this box. Uh, and then, now that's in terms of distances, right? Distance is speed times time. So set. Okay? Now you can rearrange that. There's a whole proof. You can try this out if you want to. You can get what is one guy's time in terms of the other guy's time. So the green time I'll call just plain t, and the red time, which refers to the guy inside the moving vehicle, the train, the rocket, whatever, I'll call t naught. Okay. So what is guy inside the train versus the guy outside the train? Okay. They're going to experience different passages of time. Right. Now, does this happen every time you jump in your car and drive north on I-95 at 70 miles an hour? Well, yes, but it's such a subtle effect that you would never notice this just with your own brain or with a like a quartz watch. Okay, because guys, look at the square root down here. Oh, well, we'll start with first something called the correspondence principle. Right, does this align with just everyday like, common sense? Right, which is that you're driving around on I-95 and everybody agrees that how much time has passed, like 3 hours, 3 hours, whatever. Right? Uh, because what if v is equal to zero? Like, isn't it true that all of us right now are not moving relative to each other? So we all agree on how much time is passing. Okay, let's try this out. Guys, what is zero divided by speed of light squared? Zero. What's one minus zero? One. What's the square root of one? One. And then t naught divided by one would just be t naught. So do you guys see t would be t naught? Okay, so everybody agrees on how much time has passed as long as nobody's in motion. Okay, but if you get one guy accelerating into being in motion, right, so they both start together and one guy takes off. Right? Then this kicks in play. Now, if you plug in like 70 miles an hour here, guys, compared to the speed of light, it's like 10 to the 8 meters per second. It's so tiny that this fraction is very, 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 very close to zero. It's not zero exactly, but it's very close. Even the fastest that people kind of move relative to each other, you get some guy up in the International Space Station, he's orbiting the Earth once every 90 minutes. Even that, you plug it in here, and this dilation effect is so tiny that you would really need atomic clocks to be able to measure it. Right? And they have. Sometimes to take atomic clocks into the International Space Station or into GPS satellites, and that actually does matter. That actually is one practical application of this whole theory, by the way, is GPS would not actually work, except they have to adjust the atomic clocks inside the GPS satellites, right, according to this theory of relativity, right? Because time takes a tiny, tiny bit different for different reasons, including motion. Right. So here, next slide. I'm going to refer to like a rocket twin and an Earth twin. Do you guys hear something called a twin paradox? Have you guys ever heard that phrase, twin paradox? Yeah, that's what this leads into. So the twin paradox is suppose you have you have two twins, right? And they're the same age, whatever. Right? You got one guy stays on Earth, and then I'll call him Earth twin. You got one guy hops in a rocket. I'll call him rocket twin. You know, the guy in the rocket, suppose he's flying around very, very close to the speed of light. So maybe the c is like 99% the speed of light. Okay, now that would definitely be a relativistic speed. And then if you ran this fraction, how about this? Let's try this out. What if v is getting pretty close to c? Would this fraction be getting pretty close to 1? Maybe it's like 0.9 or something. Okay, because what's 1 minus 0.9? 1 minus 0.9, is that like 0.1? Right, and the square root of 0.1, well, it would be what, here, let me see. What is the square root of 0.1? My calculator's telling me like 0.31. Yeah, that's about right. 0.3 something. Okay. All right. So, guys, what is if T naught? Let's say rocket twin's been flying around for a year. What is 1 year divided by 0.3? I'll call it. That's like 3 years. So 1 year to rocket twin could be 3 years to Earth twin. So he comes back and says, "Oh, I've been flying around for a year," and his brother Earth twin says, "No, actually, it's been 3 years. It's been a long time." Okay? Now you take this to an extreme, like 99.9% speed of light. Maybe rocket twin thinks he's flying around for a year, comes back and his brother on Earth is like, "It's been 50 years." So their age is totally mismatched. That's how much time has passed. Okay, this is called the twin paradox. You want to see that? Right. Now, think about it though. Suppose there was some star several light years away, and you sent a rocket to it, and we're based on Earth, we're watching through a telescope, watching this rocket goes towards Earth. We know it's going to take, even if you travel at like half the speed of light, it's going to take several years to reach it, right? But you know now, if you're on board that rocket, speeding up close to the speed of light, that not as much time passes in your frame of reference. What that has to mean, consequentially, is that the distance to your destination is not as far. So that's this length contraction. You guys see this length contraction down here? And there's fun stuff you can do with that too. There's this fun thought experiment with like a train going through the tunnel and what's longer, the tunnel or the train. But try to really condense this down for you guys today. Right? There's also this momentum dilation. So you get all these strange relativistic effects. Again, like in our everyday motion, you would never really come up against these. Okay? But if you take things to an extreme case, then you do. And an example of this momentum dilation that particle physicists run into all the time is this particle smasher over in Switzerland. It's called the Large Hadron Collider. Okay? So they'll take protons. So they'll take hydrogen atoms, strip off the electrons. So they have the protons. And they'll speed them up like 99.9 something percent the speed of light. Now, when they do that, this is a giant circular synchrotron. So they're steering this around with magnets, because otherwise, Newton's first law, I think it just wants to go in straight lines. So they got to steer it with magnets. Okay? Okay? But the more massive the particle is, the stronger the magnetic field they need. Okay? If they put in, say, like 1 gram of particles, then it might show up as like several grams of particles, right? Or like 50 grams of particles, right? Or so they need strong magnetic fields to keep it in a circle, right? So that's a place they'll run to this momentum dilation. So you need relativity there, right? Right. Example. Let's look at some graphs because these are equations. But what do the graphs look like? Like here, guys. What if v went all the way up to c? Just think about what would happen, and this could be for any of these, right? So if v is equal to c, what is c squared divided by c squared? 1 exactly. What's 1 minus 1? 0. 0. Square root of 0 is 0. And anything divided by 0 is 0. Yeah, infinity or undefined, right? Infinity or undefined, right? Until you get down to this length contraction, and then you actually would be multiplying by 0. So the length would go to 0, wouldn't it? Right? Oh, I should say too, I should emphasize that if you're on board the rocket with Rocket Twin, flying at some significant percentage of the speed of light, you notice nothing strange about your own local environment. Like if you have a clock on the wall of your rocket, it looks like 1 second beats per second. Right? There's no strange length contractions inside your own vehicle. Okay? But if Earth Twin and Rocket Twin take out telescopes and they look at each other, suppose they each got a clock on their own local wall and they look at each other's clocks, then they would see each other's clocks beating at different rates. Right, so but you need to. Right, so here's the graphical version of these equations. So let's start with time. So it's time dilation. Okay. Now the Newtonian prediction is that time is the same for everyone. So that's this green dashed line right here. It doesn't matter how fast you're moving. Everybody, time must be the same for everyone, but Newton would have said, okay? And that held for a long time. Okay. But Einstein says, well, that starts out being true. Is notice if you're going maybe less than 10% the speed of light, it might be kind of hard to tell the difference, right? But faster you go, and the more you approach the speed of light, right, it really takes off. Now you really do see a difference. Okay? And anything with mass can never reach the speed of light. Right? Now, what would it be like if you were a photon? What would it be like? This is one of the thoughts that Einstein had. Okay? And one of the consequences you can see from this graph is that from the point of view of photons, you might think that maybe time doesn't even exist. Right? So it's an interesting consequences. Right? How about length contraction? Right, so in Newtonian physics, simple Newtonian physics, there is no length contraction. So everybody agrees on the length of Rocket Twin's ship or something, right? Okay. But Einstein says, well, it starts being true, maybe less than 10% of the speed of light. It's not a whole lot different. But the faster you go, that length is going to approach 0, right? So again, from Earth Twin's point of view, looking at Rocket Twin's rocket, it looks like it's shorter, shorter, shorter. Right? In fact, if it was somehow going the speed of light, the length would be 0. And from Rocket Twin's point of view, the distance across the universe would be 0. So from the point of view of photons, there's an interesting case to be made that space does not exist from the point of view of photons, right? Or anything that has no mass. Right? Right? And then here's the momentum dilation, which was kind of similar to the time dilation, like that. Now something else. Okay. Here's a Minkowski space-time diagram. Now, okay, this is kind of a fancy 3D looking one, but you guys see this x-axis, y-axis. Those represent 2 dimensions of space. You guys know space is actually 3-dimensional. Okay? There's a stripped down version of this where you can put all the spatial dimensions on one axis. Right? It makes it a little easier to look at. Right? But you guys can think sort of in 3D, right? Right? And then on the vertical axis is time, and it's really common to multiply it by c, so you get speed light. So speed times time, so you sort of have an equivalent distance axis also. So these could all be in meters, right? Meters, meters, and meters, right? And if that's true, then you can sketch out a 45-degree angle from this time axis. Well, I'll call it a time axis. Speed light times time, basically. Right. You guys see as time ticks forward, you're basically going up, right? Up, 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 up as time ticks forward, right? And photons are always going to travel along these red dashed lines, right? Because they're always photons are always traveling at the speed of light, at least through space, right? That would be true. Okay. Uh, Now, anything that could affect you up to the point that you are sitting in this room, it has to be in this past cone, right? Anything that's like outside here is the light information can never travel faster than the speed of light. So anything outside this cone can never affect you. Anything that you can affect in the universe going forward has to be in this future cone. So something that happens out here, like for example, suppose we send somebody to Mars one day, or I don't know, maybe a couple decades, right? And you want to send them an email. It's going to take several minutes for that email to reach them on Mars. It's not going to reach them in like half a second because that would be like out here. So what can you affect? What can affect you and what can you affect, right? So Minkowski space-time. And there's a lot of fun thought experiments you can do with this. So any of these slides I show, if you're more curious about it, like you want to see what's twin paradox or what's Minkowski space-time, you can go to Google, YouTube, and type and see all kind of fun experiments related to all these things. Okay. Now, something else that falls out of special relativity, and this is all stuff that Einstein published in 1905, is mass energy equivalence. Now, it's a whole, hang on, let me pause this. Get this phone call. Oh, no, let's try this again. All right, so there's a whole proof leads up to this. I'm just showing you guys the last couple steps, but I know everybody's seen this formula, E equals mc squared. Right, so this is called mass energy equivalence. So E stands for energy, M stands for mass, and C is the speed of light. No, it's being squared. Just the speed of light itself is being squared, right? Not the M. Right? This is the energy of nuclear reactions. Now, you guys remember you took a class called chemistry, and one of the important founding points for chemistry was something called conservation of mass, right? So if you add up all the mass of your reactants and all the mass of your products post-chemical reaction, you get the same mass, right? So mass doesn't disappear, right? Well, when you run into nuclear reactions, that's no longer the case, right? So if you have some uranium and you put that in a nuclear reactor, right, and get energy out of that, right? It looks like there's missing mass. And how much? Well, if you take that missing mass multiplied by the speed of light squared, it's equal to the energy that you can get out of the nuclear reactor. Okay, right? Right, so mass energy equivalent. Now, if you say what's the mass of a proton or a neutron, which is called a nucleon, it's actually different in different atoms, right? There's an upside down version of this graph. I think it's framed the way that I just said that. Right? Or if you look at binding energy per nucleon, right, it's also different per atom. So if you start with hydrogen, right, and you go to helium, do you guys see there's a huge jump up here, right? Or if you start with uranium and go like towards iron, right, it jumps up a little bit. Right? Now, here's a fission, right? So if you take a neutron and bombard a U-235 atom, which is one specific isotope of uranium, which is like less than 1% of uranium that you mine out of the ground is this stuff, but you can right, get the U-235 isotope. And that will break apart into krypton barium. Well, this is one of the reactions. There's some other ones too, but this is like a really common one. It release more neutrons, and then you can get a chain reaction going. Right, release a bunch of energy at once. That's a fission process. So this height difference sort of represents the energy you can get out of fission. Okay? But you guys see there's a much bigger jump from hydrogen to helium. Okay? It's hundreds of times bigger. I might round that to about 1,000 times the jump going from hydrogen to helium. It's going from like uranium to like, krypton barium. Okay? So that's a fusion process. Now, fusion, you're starting with these, well, this is deuterium and tritium. So it's isotopes of hydrogen. Right? Most hydrogen doesn't have a nucleus, but sorry, doesn't have a neutron. I meant to say doesn't have a neutron. This one has one neutron. This has two neutrons. It's just got some extra neutrons. Okay, and then you can fuse these together, and it'll create helium and more neutrons and lots and lots and lots of energy. Okay? Now, all our modern day power plants are all these fission plants, and fusion. Well, that's a developing technology, so we're not quite there yet. Okay? But fusion has a lot of advantages. Right? One, it's like almost 1,000 times the energy. Right? Also, there's a lot less radioactive byproduct from this, right? Because one of the problems with nuclear power plants as well, what do you do with the nuclear waste, right? You have to store that for maybe like tens of thousands of years. And how do you tell people 10,000 years from now, like, stay away from this place because you get sick, radiation poisoning, right? But fusion's a lot cleaner. Okay? Fusion that isn't the energy of stars, right? So our sun, it's all fusion, right? All right, so I got that. All right, so that was all from about 1905. Einstein published all these ideas. Right now, fast forward to I think about 1915, 16, somewhere there. He extends this and incorporates gravity into his model of relativity. So now we're getting to something called general relativity. Right? And it starts with this thought. It was imagine a guy falls off a building, and as he's in free fall, that would be an identical experience to be out in deep space, just floating around where there's no gravitational fields, right? And if that's true, Einstein started to think about gravity actually being different from the other forces, like contact forces. Like if you pick something up, isn't that electrons pushing against electrons? You pick something up, right? Uh, Einstein says, actually, this guy who's in free fall, who would say, oh, well, he must be accelerating at 9.8 meters per second squared. Actually, Einstein said he's not accelerating because his experience is identical to this guy out in deep space. What's really going on is that gravity is not actually a force, but it's really an artifact of the warping of space time. Right? So the larger mass you have, then the more it warps space time. Right? And we perceive that as what think of like a force or a gravitational field. Right. And then it simplifies to Newton's law. So you can say like, oh, the gravitational force between the Earth and the Moon, F equals G and M over R squared. Well, Einstein says, actually, it looks like that, and that's an approximation, but that's not strictly true. And if you get really huge gravity fields like near a black hole, then doesn't hold so much, right? Even if you look at the orbit of the planet Mercury around the sun, it doesn't. The orbit of the planet Mercury does not follow exactly what Kepler and Newton said it should do. Uh, but if you follow Einstein's physics that comes out of starting with the slide and going forward, it actually matches the orbit of the planet Mercury in some of these extreme cases a bit better. Okay. Okay. Oh, how about this? How about just standing on ground? Right, it feels like we're all at rest right now, right? Okay. But Einstein was saying, actually, that would be identical to if you were in a rocket, again, out in deep space, there's no gravitational force nearby, and you were accelerating upwards at 9.8 meters per second squared. Like you would not be able to tell the difference between those two. So you have to think of it being that way. And all of us right now, sitting at rest on Earth, well, we think we're at rest, but really it's more like this, right? And so kind of like, well, here, let you guys think about that. That's right. So that leads to general relativity. So you can bring in like what's the effect of gravitation on also time. So it turns out that gravity fields also slow down time, kind of like motion slows down time for the twin paradox example, right? Right. Now here's where I got to talk about GPS satellites. Could you guys imagine there's a bunch of GPS satellites that going around the Earth, right? And they're sending out signals, and your cell phone could be picking up these signals, and there might be like I think it's like 24 or 36 satellites out here, something like that, right? So they're going around. And your phone is picking up these signals from these satellites, which tells you exactly how far away you are from these satellites. Now you can use triangulation. So if your phone's getting, say, like 3 or 4 or 5 signals from these satellites, you say, okay, I must be exactly that far from the satellite, that far from that one, that far from that one. They can pinpoint down to the nearest like square meter exactly where you are on the surface of Earth. That's how GPS works. Okay? Right. But this would not work unless you actually adjusted the atomic clocks inside those satellites. You have to adjust it for 2 reasons: special relativity and general relativity. So the fact that these uh, satellites are whizzing by so fast is going to, think about twin paradox, would slow down their clocks relative to us. So they have to speed them up a little bit. Right? But there's a competing effect. The fact that they're so far out means they get less gravity compared to Earth, compared to the surface of Earth, which means that the clocks would be speeding up faster, and that causes the opposite. So they have to slow them down. Right? I think overall they have to end up slowing down because those are 2 competing effects, right? They do opposite things, and one effect is more dominant than the other. But if you did not take into account those 2 effects from special and general relativity, then GPS would be off by I forget exactly the number, but I think it's like several kilometers every day, something like that. So you might show up and like, oh, it looks like I'm in Tampa, by the end of the week. It wouldn't make any sense. Okay. Okay. Now, if you look out in the wider universe, there's some fun effects from uh, well, here. So there are these 2 mysteries out in the universe, and they have similar looking names, but they're actually opposite effects. So one's called dark matter and one's dark energy. Right. So if you look at how fast our galaxy is rotating, like if you follow say like Kepler laws, or you predict say like this dashed line down here. Right? But the actual observation is more like a constant speed as a function of distance. So like these stars out here are moving as fast as these stars here, which doesn't really make any sense from the point of view of say like our solar system, right? What could be causing that? And also there's gravitational lensing effects. Let's see if I get a photograph. I think I have a photograph somewhere. Should pick this up. All right, hang on. I'm real close right here of this gravitational lensing effect. There we go. Okay, I'm gonna flip my screen here and show you guys what this actually looks like. Right. What do we mean by gravitational lensing? There, come on, point, point. Okay. So you guys see this ring right here? See this ring? This is actually a galaxy, which is probably just a normal looking galaxy, right? But there's some large amount of mass that we don't really know about, can't explain, right? That's acting sort of like a giant spherical lens, and it makes this look like a ring to us. So it's called an Einstein ring. Right? Now, again, if you were like next to this galaxy, it would just look like a normal galaxy. But from our point of view, there's like some blob of what's called dark matter between us and this thing. Yeah, we don't know what it is, or I mean, there's some ideas, but it's causing this lensing effect. So got that. Uh, so cause all these things. Now, dark energy is kind of an opposite phenomenon. Like if you look at space expanding, now people have known that space is expanding since the 1920s. There were different ideas about like what is space doing? Is space static, or as it grows, does it do like new stars come into existence? So there are different ideas. But Edwin Hubble was looking at distant galaxies and noticed that they were all redshifted. Do you guys know about Doppler effect? Did I tell you guys about that? So a car goes by on the road, so it's like, you hear that pitch shift. But if you're inside the car, you don't hear pitch shift, just if you're standing on the sidewalk. Now, light, similar effect. And the more stretched out the light gets, it gets like more red. Right? And the more condensed it gets more blue. It's called blue shifting versus red shifting. And the further away galaxies are, the more red shifted they are, which says they're moving away faster and faster. So we've known this for a long time. There's this universal expansion. There is no center of the universe. Like when you take Big Bang model, like if you run the clock backwards, you say, oh, it's like everything is about same place, same time, about 14 billion years ago. Right? Now there is no center of the universe. It's not like there's a central node and everything's racing away from that. There's this cosmological principle. So no matter where you are in the universe, everything is racing away from you. Right? You could be in some completely different galaxy, somewhere completely else in the universe. Everything is moving away from everything. Okay. Uh, Now, in the 1990s, astronomers set out to say, okay, well, what's the slowdown rate of this? Because I mean, yeah, we know everything's moving away from each other, but it seems like everything should gravitationally attract back together. Right? Is the Earth, is the universe going to end in a big crunch, or is everything going to race away forever, or what's going to happen? And what they found is that as time is passing on, as time is marching forward, the expansion of the universe is actually speeding up. Now, nobody was looking for this or expecting this or hypothesizing this, but that's just what the data was showing. And actually, different teams of astronomers independently found this to be the case. This was around like 1998, I think this was concluded. It actually won the Nobel Prize in physics for this. Now, what would be causing that? And nobody has any idea. This is a complete mystery. So right now, there's a term attached to this. Let's call it dark energy. And actually, you can put it as an energy equation right here. Sorry, is an energy term in this general relativity equation. Okay. Oh, I forgot to show you guys another slide. Show you guys this too. So what's like some experimental evidence for, say, like this general relativity besides this gravitational lensing? I mean, this is obvious experimental evidence too. Right? But some of the first evidence historically was actually this photograph right here, 1919 solar eclipse. So like the largest mass by far anywhere near us that could cause this gravitational lensing effect would be the sun. You guys know the sun is like more than 99% the mass of our solar system, right? So it's all in the sun, right? But you can't, during the daytime, you can't really see around the sun because it's too bright. It blocks out all the light. Can't see the stars during the day, okay? But you can during a solar eclipse specifically because our moon is just big enough where it can cover the sun, right? The moon, well, the sun's 400 times the diameter of the moon. But the sun's also exactly 400 times further away. So the star moon just barely covers the sun. Okay? And if you look right around the periphery of the sun, so like if there wasn't gravitational lensing, you might get stars that were like, say like where you couldn't see them, they might be like behind the sun, right? But if there's gravitational lensing, then it's going to bend the light towards Earth and then it will look like it's coming from somewhere else. And now this came out of my printer, so you can't see these stars very well. But if you get the original photograph, there's some star locations, you can see the locations of the stars. And they're bent out of place exactly as much as Einstein predicted according to his general relativity. So that was like some of the first hard evidence that, like if you come up with a new theory of how something works, your new theory has to be able to cover the basis of whatever previous theories worked pretty well. Like Newtonian physics worked pretty well for hundreds of years, right? There are a few cases where it's like, it's something weird off, here or there, but like French cases, but it worked pretty well. Right? But your new theory also has to be able to make predictions that the old theory wouldn't hold up to. And that's what you're seeing right there. All right, so yeah, get this here. Okay, so that's relativity. We've got a few minutes, so see what I can do with quantum here. So, favorite topic, quantum. Uh, Now, there was, of course, this classical physics, and by the end of the 19th century, there were some mismatches between what classical physics would predict and what scientists were actually seeing in lab conditions, right? And one had to do with these ovens. So they would heat up an oven and say, okay, well, we know light is waves for such reasons. Okay. And if that's true, then well, you should be able to like cram as many waves as you can to a small space. So if you heat up an oven to some temperature, okay, the spectral radiance you should be getting from this, see I've got this black curve here. So 5,000 Kelvin. So it's had an oven at that temperature, right? Should be like off the chart brightness, right? Right, but it's not off the chart brightness. We're getting like spectral radiance that's a lot smaller than that. It's actually this follows this blue curve right here. I threw on a couple other curves, but really we're just compare this black to this blue. Okay, now what could possibly explain this? Now, around the same time, there was this photoelectric effect. This was first done by Heinrich Hertz in 1887, but Einstein interpreted this in another paper they wrote in 1905. So along with his theory of relativity, all this separate idea. Right? Einstein actually published four major papers in 1905. Right? And this is actually what Einstein won the Nobel Prize for, was interpreting this photoelectric effect. Weirdly enough, not for relativity, which is actually most known for. Right? But it had to do with this. So suppose you shine a light. I'm just going to call it a solar panel, just keep it simple. Suppose you shine a light on a solar panel, maybe a red light, and you're not getting any energy from that. So say, okay, well, maybe I just make the light brighter, 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 turn up the intensity. I should get something, right? But you get nothing, nothing, nothing. Right? You're shining a light on the solar panel and you're getting no energy. But instead of making the light brighter, if you just very simply change it from red to blue, if you increase the frequency, that's like going from here to here. Do you guys see I'm increasing the frequency? Right? Now you do get something, right? In fact, if you double the frequency beyond this threshold frequency, you'll get double the energy. So there's a linear relationship that comes out of this. I have actual experimental data for this too. I know it's like a cartoon version, but there's actually experimental data that looks pretty much exactly like that too. And so what could possibly explain that? Now, Einstein's interpretation, it's what he won his Nobel Prize for in physics, was that light also has particle-like properties. So that it's kind of like a like garden hose analogy. If you have a couple of garden hoses, you roll in marbles down those. Let's say the marbles represent like packets of energy, like photons, right? Well, if you roll them twice as frequently, that would represent twice the number of marbles you're getting out. It's like twice the energy. Okay? And that's aligns exactly with this, right? If you double the frequency beyond the threshold, you get double the energy. So light has particle effects. So it's called, and the slope of this is called h. This is Planck's constant. That's like the energy per photon, which is a tiny, tiny, tiny number. You guys see that 10 to the minus 34? Now we're stepping into quantum mechanics. So we're getting saying like, what's the physics of like extremely small things, like down to the atomic size? And physics is really wacky for lots of reasons, and I've got lots of slides queued about this. Right? One is that, guys, if you look at your phone screen, it looks all fluid. Suppose you're watching a video, it looks like kind of real life, right? But if you zoom down really, really tiny, like if you're an ant crawling around your phone screen, is it really like pixelated? Okay. Now, is the universe kind of like that too? Well, if you talk to quantum physicists, they say kind of yeah. Right? When you get down this Planck length or this Planck time, doesn't really make sense to subdivide these units anymore for some reasons, right? Like that. Right, so I might come back to this one. Right. Okay, we got this wave particle duality now. Now that was true for light. So is light a particle or is light a wave? Well, now we got photoelectric effect, combined with the double slit experiment. Light's kind of both, has this duality. Now, does anything else have this duality? Actually, you can get the wavelength of any particle. Just take Planck's constant, divide by the momentum of the particle, and this matters enough for very small masses like electrons. So electrons actually have this dual nature, and that actually explains. Does this look familiar from a chemistry textbook? This electron configuration. Okay, now why is that this electron configuration? You can explain this with quantum mechanics. It has to do with the wave nature of electrons. Electrons are actually more like waves than they are like particles. Right? Why do electrons only occupy certain energy levels, certain orbital levels? That's what all this electron configuration is. Okay? The explanation goes that to complete an orbit, it needs to be a complete number of wavelengths. This is a cartoon version. If you look at the actual orbitals, they're all 3D and crazy looking, but it's really a cartoonized version. Okay? It has to be some complete number of wavelengths. Okay? That would explain these orbital levels. Okay? All right. Yeah, there's a lot more fun part of this presentation. I might say this for, yeah, right. I got some other ideas for, I know we just got a few days left here, but we're getting short on time. So see what we'll do for next few days. But yeah, you guys have a good rest of your day, and yeah, we'll do some fun stuff next few days.